So now we want to prove this weak approximation theorem that guarantees the existence of a function z, or in this statement x, that satisfies this property. And as I mentioned before, the proof is technical. Actually, it contains 3 steps and 1 conclusion. So this is why I need to divide it in 2 steps. I need to divide it. I need to divide the proof in 2 video records. And in this video, we consider 2 steps. The first step, so here before, let me fix the notation. For given distinct places, let me denote the discrete, corresponding discrete valuation map with Vi. And in the first step, if we are given n distinct places, P1 up to Pn, there's a function u which has 0 at P1 and poles for the remaining distinct places. So our first claim is to prove the existence of such a function. And we prove it over induction, by induction over n. By induction over n. And for the initial step, let me consider to do 2 distinct discrete valuation maps which are corresponding to given places, or correspondingly we can also consider discrete valuation rings. And since they are pairwise distinct, and moreover the valuation rings are the maximal proper subrings, we know that these valuation rings cannot be equal to each other. So neither OPX lies in OP1 lies in OP2, nor OP2 is a subset of OP1. And this allows us to consider, since we don't have inclusion, so that means there exists an element in O1. Let me denote it Y1. But this is not an element in OP. And similarly from here, we may consider a function Y2, which lies in OP2, but not an element in OP1. Or equivalently, again by the correspondence of the discrete valuation rings and maps, we can state these conditions as there exists a function y1 such that v of 1 y1 is non-negative, but its image under the discrete valuation map v2 is negative. And correspondingly, we can write v2 of y2. This should be bigger than or equal to 0. And y1, y2, or y2 has pole at p1. And now our claim is that if we consider the fraction of these 2 functions, y1 and y2, this gives us desired function for the inductive step. So that means when we compute the v of 1 of y1 over y2 by using the properties of the discrete valuation map, since we know that this is bigger than or equal to 0, and since this is negative this term should be strictly bigger than 0. So that means y1 over y2 has 0 at p1. And when we evaluated it at p2, again by the properties of the discrete valuation map, we see that since v2 of y1 is negative, and since this is bigger than or equal to 0, but for the minus, we see that this is indeed negative integer. So this u gives us the desired function for the inductive step. And now we suppose that the statement holds for n-1 distinct places, and we want to conclude that this is also true for n distinct places. And by the assumption, let me suppose that there exists a function y which has 0 at p1 and poles for the other places at the other places. And if this function has pole at pn, we get the desired, and there's nothing to prove. But if v and y does not have a pole at pn, and since v1 and vn are pairwise distinct, by the case n equal to 2, we know the existence of z that has 0 at p1 and pole at pn. And in this case, if we set the function u as y plus z to the r for some r from natural numbers, it will be allows us to apply the strict triangle equality, which I will mention in a minute. Our claim is that u is the desired function for this property, which satisfies this property. And to see that, we come to evaluation of y plus z to the r. And since we have chosen r that allows us to apply the strict triangle inequality in this step, p of 1 of this function is equal to the minimum of p of each one. And since for y, we know that it has a pole at p1 because we suppose the existence of such a function. And since we also consider that this satisfies this property, and since we consider also that there is a natural number, we see that v1 of u is strictly positive. And for the other valuation maps, again by the strict triangle inequality, and by our assumptions such that Vi of y is negative, and Vi z, I mean, if this is negative, actually we don't need to compute the Vi of z, even though it's positive or negative, this valuation should be negative. And we can see for each cases, we can see the existence of such a functions that satisfies this desired property. So in the second proof, in the second step of the proof, our claims that for given integers are i's, and again pairwise distinct places or the corresponding discrete valuation maps, there exists a function omega such that omega minus 1 has, I mean, actually, since these are integers, we can't conclude that it has zeros or poles, but valuation v1 of omega minus 1 is bigger than r1, and vi of omega is bigger than ri. And first, let me note that from the first step, we can choose a function u, which has 0 at p1 and poles at the other places pi's. And let me set a function omega 1 plus inverse of the 1 plus u to the s for sufficiently large natural number s. Now I will explain what does I want to mean by the sufficiently large, particularly when doing the computations, because here our claims that omega is the desired function, so we need to check v of omega minus 1. That means 1 over 1 plus u to the s minus 1. By making the denominator equal, and also by the arithmetic of the discrete valuation map. Since v of u, this is, sorry, by the way, this is not going to be y. This is y1u, y of u. And since y1 of u, this integer is strictly positive, and since we choose sufficiently large integer s, even though if we are not able to have a guess any idea on this integer, for sufficiently large s, is it possible to bound it by the given r1. And for the other discrete valuation maps, again by the simple arithmetic of the discrete valuation maps, And since this is also possible to choose S, that will allows us the strict triangle inequality for this valuation. Here note that this constant and is going to be 0. And this is equal to S time VIU, and U is negative. For sufficiently large S, this is going to be positive integer, and it's possible to guarantee that it is strictly bigger than the given integer Ri. And in the next video, we will prove that for given pairwise distinct places and the integers are i's, and given n functions y from y1 to yn, we show the existence of a function z such that vi of z minus yi are strictly bigger than the given integers ri.